There's now a connection between quantum computing and black holes.
Ready to discover what was witnessed inside a supermassive black hole? Brian Greene's remarkable discoveries reveal the mysterious realm inside these cosmic titans. Join us on a scientific adventure to discover the inconceivable treasures of the abyss. For decades, scientists' fascination with the idea of our universe living inside a black hole has prompted deep conversations and speculation about the nature of our reality. General relativity and quantum mechanics, two pillars of modern physics, are the source of the idea. It is possible that our universe exists within the event horizon of a black hole, which serves as the edge of our cosmic horizon. It's possible that inside this black hole, the laws of physics as we know them would radically change, throwing our understanding of space, time, and matter into question. Although this theory is still in its early stages of development, it presents an exciting new way of thinking about black holes and the cosmos. Investigating the idea that we could survive within a black hole forces us to question our very existence and to go deeper into the laws that govern our universe. As physicists seek a unifying explanation of everything, the idea that our universe could fit inside a black hole exemplifies their insatiable curiosity and creative spirit. Recently, physicist Brian Greene has made comments that have caused a stir by saying that the present theories on which they are built are faulty. Renowned for his contributions to string theory and the study of the universe's fabric, Greene argues that we are not only viewers of the cosmos, but rather inhabitants within a huge black hole. Greene's provocative idea proposes that our view of the cosmos as an infinite space ruled by known physical principles is an illusion. Instead, he claims that existing explanations for the world we live in are inadequate. Greene's theory of a world in which we exist inside a black hole calls into question long-held beliefs about the nature of space, time, and the Big Bang. There will be a heated discussion about Greene's proposal among scientists and cosmologists. His groundbreaking assertions have been met with skepticism, however, and this points to the importance of both empirical evidence and theoretical developments in our quest to understand the meaning of life. Regardless of the final verdict, Greene's audacious ideas will act as a catalyst for reevaluating long-held scientific hypotheses, opening the door to new ideas and more in-depth investigations into the universe's mysteries. Throughout his distinguished career, Greene has made seminal findings that expand our comprehension of reality's most fundamental elements. Through his studies, we now have a clearer understanding of the complex structure of string theory and its potential to unify nature's fundamental forces. His groundbreaking work has sparked the interest of both his fellow scientists and the general public. The connection between black holes and the creation of new universes has been the subject of many fascinating speculations. In their mysterious depths, black holes may give rise to totally new worlds, according to one theory. From the extreme gravity and singularities at the center of black holes, these baby universes would form and grow into their own realities. The idea that the cosmos itself is contained within a massive black hole is another popular one. This theory proposes that the black hole is actually a portal to another universe, with the entire observable universe contained within its event horizon. Another possibility is that our universe was created by a black hole in another universe. These extremely huge black holes may have been the catalyst for the Big Bang that gave rise to the universe as we know it today, with all its galaxies, stars, and planets. Although these hypotheses are still just speculation, they spark our curiosity and offer a window into the unfathomable mysteries of black holes and the Big Bang. The study of the underlying rules and principles that control the way matter and energy behave in the modern universe is known as physics. The Standard Model, general relativity, and quantum mechanics are all included. The probabilistic character of particles and the wave-particle duality were revealed by quantum physics, completely altering our conception of the microscopic universe. The ideas of superposition and entanglement were introduced, which cast doubt on traditional determinism. The theory of general relativity, introduced by Albert Einstein, defines gravity as the distortion of space-time brought about by large bodies. It accurately predicts phenomena like gravitational waves and explains the motion of heavenly bodies. The Standard Model is an all-encompassing framework that characterizes the fundamental particles and their interactions via electromagnetic, weak, and strong fundamental forces. It successfully describes a wide variety of experimental facts while unifying electromagnetic and weak forces. The development of revolutionary technologies like semiconductors, lasers, and particle accelerators can be directly attributed to the insights provided by these theories. To better understand the cosmos and its underlying nature, modern physics continues to push the boundaries of knowledge. The subatomic and atomic worlds are explored in great detail by the principles of quantum mechanics. To make reliable predictions at this scale, a new framework must be developed. As standard Newtonian mechanics breaks down, the wave-particle duality is a central tenet of quantum physics. Particles like electrons and photons, it says, have characteristics of both waves and particles. Because of their dual nature, these particles can display wave-like properties like interference and diffraction. The mathematical framework of wave functions captures the wave-particle duality perfectly by describing the odds of finding particles in various states. The idea of superposition, in which particles can concurrently exist in different states, is also fascinating. This indicates that a particle can exist in a probabilistically infinite number of states before any measurement is taken. When a particle is measured, its state collapses into a single number. To investigate and explain phenomena that cannot be explained by classical physics, scientists have turned to quantum mechanics, which lays the groundwork for comprehending the complex and, at times, paradoxical behavior of particles at the tiny level. Albert Einstein's general relativity explains gravity as space-time curvature caused by matter and energy. According to this theory, huge objects like planets and stars bend space-time, causing gravity. The theory accurately describes gravity, including planet motion and light bending by huge objects. General relativity fails in severe situations like black holes or the early cosmos. These scenarios include extreme densities and energy levels, which violate general relativity. A theory of quantum gravity, which combines quantum mechanics, is needed to adequately understand these occurrences because the theory breaks down at such extremes. Scientists are currently investigating ideas like string theory, loop quantum gravity, and others to find a unified theory that integrates general relativity and quantum mechanics to understand gravity under extreme conditions. The Standard Model of particle physics provides deep insights into matter's underlying elements and forces. 3 of the 4 fundamental forces, electromagnetic, weak, and strong nuclear, are described. It also introduces quarks, leptons, and gauge bosons, which shape the universe. Despite its successes, the Standard Model has some shortcomings. It cannot explain dark matter and dark energy, which make up a large part of the universe. The traditional model cannot describe these perplexing entities since they only interact via gravitational force. Physicists are researching supersymmetry and string theory beyond the Standard Model to close this gap. These efforts to seek a more complete theory of everything by expanding our knowledge of the universe and illuminating dark matter and dark energy. Physicists struggle to unify gravity with the other fundamental forces. Despite advances in comprehending the various forces of nature, integrating gravity into the broad framework of fundamental interactions has been difficult. Einstein's general theory of relativity distinguishes gravity from electromagnetism, the weak nuclear force, and the strong nuclear force. Quantum field theory has unified the later 3 forces, but gravity has not. The dramatic difference between gravity's classical nature and the other force's quantum nature is the fundamental difficulty. Quantum gravity, which reconciles gravity with quantum physics, is still being developed. String theory and loop quantum gravity are promising approaches, but a solution remains elusive. The unification of gravity with the other four forces would provide fundamental knowledge of the universe, leading to discoveries in cosmology, particle physics, and the early universe. Physicists keep trying to understand gravity and integrate it into a unified theory.